Hello everyone. Today we're going to be doing a code along video where I'm making this flow field effect. So we've got some particles that are following a noise map generated with Perlin Noise, and you can see it can follow any noise map that you give it. So if you want to see how this code was written, come along for the journey. Okay, so we've just got a blank P5.js sketch here. The first thing we're going to do is we're going to create an array for the particles that we've got. Now I'm thinking we don't need to create a class or anything for these particles. We can just have an array of vectors, and we'll use those vectors to track where the particles are on the screen. They don't need anything more complex than that for this. So we'll just start off with an array, and we'll say, I guess we'll say how many particles we want. So we'll start off with 100, see how that goes. So the first thing we want to do is put some vectors into that list of particles. So we'll create a for loop. And we'll go up to the number that we've just specified, and I++. And then what we're going to do is, I guess we'll just place them randomly all along anywhere on the screen. So we'll say p.push create vector, and then we just want a random number somewhere in the width for the x, and then a random number somewhere in the height for the y. And then I think that's all we need to do to initialize all the particles. So then what we want to do is we actually want to be able to see them. So I think for this one, we might set the background to 0, and then we'll have the particles show up as white. So we'll say for let I equals 0. This is the same as the for loop above. Num, and then, I++. And then instead of pushing a new vector to it, what we're going to say is we want to draw a little dot on the screen at the point of this vector. So we'll just say point at, actually what we might do, just so we don't have to keep getting it, is we'll say let, I've already used p, let c equal p I. This is very bad variable naming. In fact, we might say particles just to be good. All right, and then we can say let p equals particles I, and then we want to put a point on the screen at p.x and p.y. So if we run this now, we should see, we probably need to set the, I think it's the stroke to white, so that they actually show up on the screen. And there you can see, if we run this, you get particles just on the screen in a random location each time. So now what we want to do is we actually want to make these move based on the noise function. So the noise function, I've talked about this before in a previous video, which you can clink, it's probably over my face, about generating random terrain, but we can use this noise to do other stuff as well. So it's based on, in P5.js, the noise function is based on Perlin Noise, but there's some other similar types of noise that you can use, like open simplex noise is a good one. But essentially what this does is this function just creates some smooth noise values over an n-dimensional space. So we're going to use 2-dimensional, and it just gives you a value between 0 and 1, but the points around a point will be a similar value. So say we've chosen this point here and it gives us a value of 0.5. The one next to it might give us 0.51, and the one to the right of it might give us 0.49, something like that. So you get smooth gradients between the noise. So what we're going to do is we're going to map the value that we get from 0 to 1, and we're going to map it to an angle that this particle is then going to move in. So we might just create an update function. Well, actually, because this isn't a very complex sketch, what we might be able to do is actually just do it in the same loop that we're drawing them on the screen. So after we've moved them, after we've drawn them, we're going to move them. So we're just going to say, well, first we need to get the angle, first we need to get the noise value and then convert that to an angle. So we'll say let n equal the noise at p.x, p.y. Now, actually, this won't be very good. What we're going to have to do is we're actually going to have to times this by a value that we're going to call the noise scale. And we're going to set that to be 0.01 or something. We'll fine tune this later. But basically, what we have to do is we have to scale down the values that we're picking because of the way that Perlin Noise works. So if we left it as just p.y and p.x, it would actually be super grainy because we're too zoomed out on the noise, whereas this noise scale, since it's below 1, we're going to be zooming in on the noise, so it's a less random looking thing and it's a lot smoother. So you can have a fiddle with this number if you want, and you'll see the effects it has. So we've got this n value which is between 0 and 1, and now what we need to do is we need to map that. So it goes from 0 to 1, and we want to map it between 0 and 2 times pi, because we're working in radians, and 2 pi is a full revolution. And in fact, we definitely don't need the map function for this, because we're just getting a value between 0 and 1. So what we can say is a equals tau, which is 2 times pi, and we're timesing that by the n. And then what we can say is p.x plus equals cos of the angle, and p.y plus equals the sine of the angle. Now this is just some trigonometry, so we're converting an angle into an x and y, and if you had a speed variable, you'd times it by the speed here, but I'm just going to keep it as just the straight cos and sine values, so that, because we don't want the particles flying around the screen super fast. So if we run this, you can see what's happening is they're all converging on these noise paths, but as you can see, the particles are just leaving the screen and then nothing else is happening. So what we're also going to do is we're going to write a little function that checks if the particle is, or a vertex, sorry, not a vertex, a vector is off the screen. So we'll just say function on screen, and we'll pass in a vector. And so all we need to do is we'll just check that the v.x is greater than or equal to 0, and the v.x is less than or equal to width. And that takes care of, so the x has to be between 0 and the width. And then we also just do the same thing for the height, for the y variable. So v.y is greater than or equal to 0, and v.y is less than or equal to height. And so this should just tell us if the vector is on the screen or not. So we'll just say if not on screen p, then what we'll do is we'll just give it a new random position on the screen. So if they go off the bounds, they'll just come back in to the middle of the screen somewhere. So then we say p.x equals random width, and p.y equals random height. So now when we run this, we should see that we're getting new particles spawning back in the middle of the screen once they've gone off. All right, and so I think our particle count is way too low to actually see anything cool. So we'll bump it up by 10, and you can see already that this effect is starting to take place. So what's happening is they're all converging on these routes in the noise map. So I think we're just about there. The last thing that we might do is give them a little trail so you can see where they've all been more clearly. So one easy way of doing this in something like P5 is when we're setting the background, all this is essentially doing under the hood is drawing a rectangle over the whole screen with this color that we've given. So what we can actually do is also pass in an alpha component. So instead of drawing just a black square over everything, we can draw a black square but a faded one so you can actually see what was there behind it. So if we run this now, you can see that we're just drawing a bit of an overlay, and it sort of smooths out everything and you can see previous iterations. And so this is really nicely showing us the effect that we want. So we've created the flow fields. One last thing I might do is just, we've only got one set of noise values that we're seeing here, and we can never change it. So I can just quickly, if we do function mouse released, we can actually change the seed value for the noise function. And so what this does is it allows us to change the noise values that we get. So we can just say noise seed, and it takes in a number. And one thing I like to do if you just need a changing thing is you just pass in the current milliseconds, and that should give us, every time we click, you can see that they change to shift to the new noise pattern that we've got going on. And so there you go. We've created some nice and simple flow fields from Perlin Noise. So if you'd like to play around with the code, I'll put a link to this sketch in the description, and so feel free to have a play around. As I said, there are some numbers here that you can fiddle with, and yeah, enjoy. Cheers.